Very good evening to one and all. Today we move on to our next topic on our hashing algorithm techniques. So last class we completed our SHA-512, right? So this MD4 and SHA-512 coming under the category of compression function, which have been developed from the scratch. Right? There is other category of compression function that is making use of our symmetric key block ciphers to design a compression function which can be used for hashing the message. Right. So one of such technique is the whirlpool technique. So here whirlpool is an iterated cryptographic hash function. So it's not a simple iterated hash function. It is called iterated cryptographic hash function. Okay. And this is based on a scheme called Miyaguchi-Prinell scheme. That is the last scheme which we just saw. Okay, that is you'll be giving your seed value to the key, and your message will be given to the plain text inside the compression function, and the ciphertext will be taken as output, and all these values will be XORed, right, to get me the final output. So this is a Miyaguchi-Prinell scheme look like. So similar method is going to be employed here in whirlpool scheme. Okay. In whirlpool scheme, it's going to make use of a symmetric key block cipher in the place of compression function. What I'm saying here in the sense, this is your Miyaguchi-Prinell scheme which we just saw, right? So we can able to see the plain text input is given from the message block. Okay, the seed value is given to K, and the ciphertext is taken as the output here. Right. So in this one, this is the compression function, and the place of this compression function, we are using our AES algorithm. Okay, actually speaking, it's a modified AES algorithm, right? So now if we go back to our so here in our whirlpool cipher, we are going to make use of a modified AES cipher is going to be used in place of a compression function. Okay. So how this will look like in a sense, and here the original message, whatever is going to be done, should be coming as a multiple of 512 bit block. The same process is used here. Okay, if you are going to say in terms of 2 to 6 bit block, then the entire thing, including the message length bit, should come to even multiples of 2 to 6, or sorry, the entire thing should be a multiple of 512 bit block. And generally, how they will have in the sense, the 2 to 6 bit is used for our message length, means if you pad this one along with this original message, it should come to an odd multiple of 2 to 6. Thereby, if you add this one, it will become a even multiple of 2 to 6 block. Otherwise, you can able to say it a simple way, that is after padding and adding the length field should come to multiples of 512 bit, right? Here the input message blocks are given in terms of 512 bits, as well as your text node. This is a seed value, is also made up of 512 bits. Okay, and here inside this one you're having a whirlpool cipher, which is nothing but your modified AES algorithm. And here the unique feature of this whirlpool cipher in the sense, here the seed value they're going with 512 bits is made up of all number of zeros. All 512 bits will be zeros. Can anyone tell why they went for that one? Any guess? Okay, here they're going to use AES algorithm. Okay, it's light modified, lightly only modified. And this one they're supplying in terms of key, they're supplying with all zeros as a seed value. Can anyone able to guess why they went with all zeros simply? Any idea? So far, no one. Okay, so if you remember properly, one of the key features of AES algorithm which have been used to overcome DS algorithm is nothing but to mitigate the usage of weak keys, right? So all zeros is nothing but one type of weak key with respect to DS algorithm. Even if you employ this one, I'll be getting a random bits as output. So they went for all zeros here. So what are the output you're going to get here in place of ciphertext will be XOR with the plain text and your key value. This is nothing but your H0 to give me the H1 value for the next iteration. So this will be repeated and the last block will be taken as my digest value here. Right. And if you see the general idea of Whirlpool cipher, it is ditto with our AES algorithm. Okay. But with small modifications with types of sizes of plain text and keys. So here you can able to see the plain text is made of 512 bit, which is going to give me a ciphertext of 512 bit. In this case, this will be like the thing, but after hashing with other things, it will become a hash value. Sorry, after XORing with the plain text and key, the ciphertext will become a hash value, right? And here the cipher key is also made up of 512 bits. And most important thing, it is going to be given for key expander or key generator, whatever you just call, like how we have in our AES algorithm. It is going to give me an output called round keys, which is made up of again 512 bits. So in this case, this 512 bit round key will be used for your pre-round transformation, then starts your other rounds. So in this case, we have only 10 rounds, okay, like how we have in our AES 128, because we had AES 128, 196 and sorry, 192 and 256, right? So accordingly, we had different number of rounds and the cipher keys sizes varied that kind of thing. But in this case, we have fixed cipher key size, round key size, and the size of plain text, and we have pre-round transformation. Then comes our 10 more rounds before producing a ciphertext. Is it clear, guys, how this Whirlpool cipher structure works out? If it is clear, kindly raise a hand.
Excuse me, sir.
Yes, sir.
Sir, we are inputting 5 and 2-bit cipher key, so the round key will be the cipher key only, right? Like, where is the key expansion part happening?
Oh,
If you're
actually,
using this, yeah.
yeah, actually, the cipher key which are giving as a 512 bit, the same 512 bit will be used for pre-round transformation. But we have to generate K1, K2, K10. Okay, this is all different keys. We'll see. Actually, we'll be seeing how this key expansion works on. Actually, they should not use the term called expansion. They can use in terms of generator. That is, if you give 512 bit, it is going to generate another 512 bit for K1, K2 up to K10. But the same key will be used for pre-round transformation. But for other rounds, it will be generated. We'll see in the upcoming slides.
Okay, sir.
So apart from this, anyone have any doubt? Please. I think it is clear. Okay, fine. I hope everyone remember the how the state are formed. In this case, we are going to accommodate 512 bits. Okay, so totally we'll be getting 8 cross 8 matrix. Because if you remember properly, in our case we had 16 bytes, right? Here we'll be having 64 bytes. And just write here. We are going to have 64 bytes, so we'll be having a 8 cross 8 matrix. Whereas in AES we had a 4 cross 4 matrix. And in this case, we're going to have 8 cross 8 matrix. And this is how the structure of each and every round is going to look in Whirlpool cycle. It is exactly similar to our AES algorithm with slight modifications. Where the modification comes in the sense, the first step is same. So whenever you're giving input state, we are going to perform a sub-byte transformation. After sub-byte transformation, here we are going to perform shift to column. So if you compare it with the AES algorithm, we had shift to row here. Instead of shift to row, they have made shift to column. So after that, they are going to have a mixing of rows. Whereas if you go with our AES algorithm, we had mixed column here. We also had a detailed discussion on this one, right? Then comes the add round key. This is a conventional XOR addition similar to our AES algorithm. Only these two are have a slight modifications here. Right. So if you move on, like we have a sub-byte table. Okay, so we have 8 cross 8 hexadecimal bytes sitting here. So we'll be taking our sub-byte table and we'll be now everyone knows. For example, if I have 57, I'll choose 5th row and 7th column so that I can able to replace this one. Right. Similarly, this will be working on with sub-byte. Next one comes the shift column. So, but here the shift column is going to be done in a shift down process by naming the columns like column 0, 1, 2, 3, 4, 5, 6, and 7. Based on the column numbers, the shifting will happen. Okay. For example, if here in this case, I take the third column means here this last three will be taken and it will be appended here and this will be replaced here. That is, this last 3 bytes will be sitting in this first bit. If, for example, they go for 6th one, they make the last 6 bytes and will be shifted here. Next comes mixed row transformation. So this is a constant matrix used here for our multiplication. But here it is a row-wise multiplication. They take each and every row and they multiply with the constant value and they're going to change the each and every row. Okay. Next comes the add round key. Like as I said, they will take each and every byte and they'll perform an XOR operation with the add round key because here the round key is also 512 bits. So addition of these keys are very easy here. Now we come to key expansion. Actually, how Kashish asked, sir, how come we'll be producing our 512 bit for all the rounds? So when we are getting a 512 bit of cipher key, the same cipher key is used for pre-round transformation. This is the thing but our pre-round, right? It's a pre-round transformation, just addition of key. For round one, I have to generate a round key called K1. Here in key expansion, they are not going for any separate operation how we had in our AES algorithm. Instead, they are using the same round structure here. They are going with same subbyte. In this case, cyber key will be acting as my plain text. Okay, and in the process of add round key, here we have a round constant called RC1. Okay, this round constant will be present for all the 10 rounds, RC1 to RC10, and these round constants are produced using our first 8 prime numbers. How we just saw 8 prime numbers, they took the cubic root, then they'll take the decimal points, convert them into binary, then into hexa. Okay, these values will be used as a round constants for sorry, not 8 prime numbers, sorry. Okay. First 10 prime numbers. And they do the process here to get the round constants, and the output of each and every round will be used as the respective round keys in the encryption process. Is it clear, guys, regarding this key expansion process now? They're not complicating with any other separate technique, they simply went for this one, that's all. And this is the one of the round constants which is used for RC3. There is also you can able to use your sub-byte table also to get the round constant. How in the sense if you see your sub-byte table, okay, so you have a totally 8 values here. Sorry, 16. So here is from 0 to 7. This is 1 and this will come as a 1/2 and about 512, and this is another 512 bits, right? So if you consider this one as a 0, I mean this is 1. This is for 1, this is for 0, and this is as 2, and this half if you consider as a 3, then you can able to see that this is a round constant 3 actually. The same value is used here. D, E0, D7, C2. The same thing is used here. Maybe they would have used the same technique to get the sub-byte table also. Okay, like they would have took the prime numbers, then they would have created a sub-byte table. Okay. You can use this method also to find your round constants. So if you want to put everything in a summary, so we have a blocks of 512 bits. The cipher key is 512 bit, that is nothing but our seed value. We have 10 rounds. Key expansion using the same cipher method itself. Instead of round keys, we are using round constants. The same sub-byte transformation is going to give us substitution technique. Then permutation and mixing is done. And the cubic root method is used. Okay, actually here it's not first 80 prime numbers. They took only first 10 prime numbers for round constants. Right. So if you conclude this analysis of Whirlpool cipher, okay, comparative to our SHA and MD4, it is somewhat less computationally complex when I compare with those two. But generally, this is also complex technique only. But when compared to MD5 and our SHA512, this AES based Whirlpool cipher is somewhat computationally less complex, but it is resistant to many attacks. And because it is also going to produce a 512-bit message digest, same as our SHA512. So it is considered to be one of the strong cryptographic hash function. Okay, is it clear, guys? Anyone have any doubt on this one cipher? You can ask me now. If it is clear, raise your hand. On to the next topic, that is second half of our module, called message authentication code, shortly called as MAC. Okay, don't confuse this MAC with the OSI layers which you people used to study. Yeah, that is different. That is medium access control is different, and this MAC is different. So when in cryptographic point of view, when we say MAC means it means message authentication code. Okay, so what is this message authentication? Why we need this message authentication code, and what is the requirement? Because if we take our message digest, that is the digest value which we just created using our hashing algorithms, it is going to maintain the data integrity. That is going to prevent, that is, if anyone is going to change the data, it will be notified to the receiver. But it is not going to authenticate the sender of the message. Right? For example, you have Alice and is transmitting a message to Bob. Okay, if a message is like hello, okay, this hello word is not changed. It means that alone will be, I mean, the integrity of this hello is alone maintained by our digest value. Right. But what is the guarantee that Alice is the exact person who's sending the message? Who authenticates the sender? Whether he is Alice or is there anyone sitting in place of Alice and impersonating himself as Alice or not? Right. So to provide this message authentication, Alice needs to provide a proof to the Bob that he is Alice and he is not an imposter. Okay. To provide this proof, okay, we need to modify our cryptographic hash function. So generally, the cryptographic hash function is going to provide our data integrity. It can also be called as modification detection code because it is going to detect if there is any modification with respect to the message. Okay, now we have to modify this one. That is your cryptographic hash function or MDC as MAC to provide the authentication also. How it is going to be done? So this is a general way how our message digest works on. That is, if you have a message, okay, you'll be hashing. This is nothing but a hash value. So in this case, we just call the message MDC, that is modification connection code, and this is transmitted here, and we'll can able to compare the previous digest with the current digest, and it will be accepted if there is no mistake in it. Whereas if you go with the message authentication code, we have slightly modified the our hashing algorithm, nothing much. Okay, what we did in sense here, they added a secret key. Okay, a secret key which will be known with both transmitter and receiver. Actually, if you remember properly, we just saw a few applications of hashing algorithm. In a third type and fourth type, we introduced a secret key to the hashing part alone. Right, if you remember properly. So that is a message will be added with some secret key called yes, then it will be hashed. The same thing is used here, which is called as your message authentication code. The same process. So that is if you hide this one, this will look like same as our hashing algorithm. Okay, but if you add this key, so they're going to add this key with the message and they're going to perform the hashing algorithm to get the output called message authentication code. and this will be appended with the message and it will be sent here. So at the receiver end, they will take the MAC separately and they will take the message and they add the key which is already shared with the receiver. Okay. So they can able to create the MAC again and they'll compare. That way they are authenticating themselves that data is also not changed, and Alice is the authentic person who is sending the message. And this key, okay, this will be shared between these two people using some sophisticated key exchange algorithm. Okay, like how we just saw few diffie element techniques like that. There are many techniques available which will be used for exchanging these keys. Right? Is it clear, guys, how this message authentication works on? And I hope it is clear that MAC and hashing algorithm difference is clear also. If everything is clear, can you raise your hand? If you have any doubts, you can ask me now. Okay. Okay then. We'll continue. Right. So message authentication code. Okay, how we can able to add this key? There are three ways of adding the key. For example, you have the key with you. You can append it in front of the message. In front of the message and put it as a box. Otherwise, you can put your message here. Then you can append your key in the second hop also, called postfix and prefix. Otherwise, there are certain methods where they will add key both at the beginning as well as at the end. Okay. They can copy the same key like this, or they may use two different keys also at the prefix and suffix. There are two options where you can able to combine both the techniques. Right. So is it clear, guys? Now, these three different ways I've been working on. Okay, fine. So I think actually I will wrap up today's session with this one. Actually, we have a meeting by 4:30. So we will continue discussion on this Mac uh, other topics the next class, and we'll be completing our this module by next class. Okay. So anyone have any doubts?